All right, here we are for Honors Physics Electrostatics Worksheet 3 on Coulomb's Law. I'm going to take a look at problem 4. Okay, problem 4 says two positive charges that are 6 times 10 to the negative 6 coulombs, that would be 6 microcoulombs. They're separated by 0.5 meters by half a meter. Draw a force diagram for each of the charges, considering only the electrostatic forces. What's the magnitude of the force between them, and is this force repulsive or attractive? So you'd say, well, if I have two charges, they're both positive, and each of them, they tell you, is 6 microcoulombs, okay? Or, so 6 microcoulombs and 6 microcoulombs, right? And they tell you that they are half a meter apart, right? You want to know about the forces. So right away, we're going to say, look, we know if they're both positive charge, like charges repel, right? That's the fundamental rule of charge. Like charges repel, unlike charges attract. So there will be an electrical force pushing that way, and an electrical force pushing that way. And of course, the force on this guy because of that guy has got to be the same as the force on this guy because of that guy. It's Newton's third law of pair, so equal and opposite. All right, and they're repelling like that. Okay, we want to know how big that force is. So we're going to go ahead and use Coulomb's law, the equation we use for finding the force between charged particles. So we will say the electrical force is equal to K, Q1, Q2 over R squared. And yes, I really do always write the formula down before I start throwing numbers in. Always. Always, always, always. When I go back over it later, I can see what equation I was using. It's harder to tell when it's just numbers there. But not only that, but it also helps me when I'm plugging in to make sure I don't leave anything out if I can see it plugged in right beneath it. So in this case, we want to find the electrical force. We know K, that constant, 9 times 10 to the 9 newtons meters squared per coulomb squared. That is a universal constant, so it's always that value. And the Q's, you say we've got 6 microcoulombs and 6 microcoulombs. So that's 6 times 10 to the negative 6, and 6 times 10 to the negative 6. And then our distance here is a half a meter. And again, having that right above it helps me remember, oh, I got to remember to square that. All right. Those of you that know me know that I like to take the powers of 10 separate when I do a calculation like this. So running across my coefficients, I'll have 9 times 6 divided by 0.5 squared. And then I've got 10 to the minus 6, 10 to the minus 6, 10 to the positive 9, negative 6, negative 6, negative 12, 9, negative 3. Okay, now I'm ready to plunge this in my calculator. In the calculator, 9 times 36 times 4, right? Okay, and it gives me 1296. 10 to the negative 3. Hey, that means divide by 10 3 times. This is just going to be 1.296 newtons is that electrical force. You see, hey, that's a sizable force we've got here. And that's between things that are half a meter apart. Our charged particles are like this far apart, and they've got more than a newton of force between them. That's impressive. Microcoulomb is a decent charge. Okay, 6 microcoulombs, yeah, that's a decent amount of charge. Okay, that's it. That's that problem.